So I just finished implementing a first working version of runtime and compile time dependencies, both in one, using raylib as an example, and also some fixed ABI calls so you can pass structs to functions. So this is the source code. This is all you need to run this project. You see we depend on raylib. I have put raylib in the libs folder of this module, which is where the libraries go. I have defined, redeclared some of raylib's functions, and I have written a hello world that opens a window and then twiddles some colors, and you can run it. And then I have said that I want to run that function at compile time. And just to prove that it works, let's have it return I32. And I'm going to say if k1 is static, we're going to return 10. Otherwise, we're going to return 1. Okay, so comp time means 10. And we're going to say let result. And then we're just going to print line, hey, the result was result. And then we're going to do runtime result. The runtime result was RT result. All right. And when we save the file, it opens a window because the LSP is trying to compile this code. And it got to compiling this line of this block. So it did the function. It knows about this function already. It actually compiled it already to a bytecode. Let's go ahead and do this so we can look at it next time. And yeah, we're currently just in the middle of running this function. So when I close the window, we're going to compile the rest of the code. And then you notice the error goes away because the diagnostics get cleared. Every time I compile, we're going to spawn this window. Now it's the wrong color, because the struct passing ABI is not working for the dynamic calls, because there's a bug with how I'm using libffi that I'm about to fix. But let's actually run the program then. So that's compiling the program, and let's run it. So we're gonna do now I'm saying k1, which is the compiler, and this just all of these are linking with macOS frameworks so that the GUI will work. It's just a raylib thing. So some extra flags we have to pass to Clang for in the meantime. And then we're going to R for run. And then dot means this folder, this project. Run dot. So, and we have this is the compile time execution. And let's look at the function. So we asked for a debug dump of run. So here's our run function. And on the right, we can see, let me move my face. On the right, we can see, let's leave our beautiful compile time. Do I have 2 open? No, okay. Let's leave this open and then let's look. So it's a lot like LLVM-IR, but this is the K1 IR, the K1 bytecode. And there's some things it's doing, like return value placement that lets it emit fewer instructions, and a couple other kind of unique things to do with the metaprogramming. But apart from that, it's basically LLVM-IR where some sizes are fixed. But you know, here's the source code on the right, and we've got basic blocks. So here's our loop, enter while condition, this jump B1, we'll jump to B1. Yeah, that's an unconditional jump. We just stored 0 into I2768, which is let I equal 0, right? Does that make sense? Here we go, assigned less than. We're gonna keep going, and then we got some fun things. We got some calls. Call extern raylib draw text. Function ID is 1347, and then these are our parameters. Global 39 is that color gray. These are immediate data values that are stored in the instruction themselves. This is a register value. It's this one. Field access no copy. It looks like yes. Grabbing the pointer off of the congrats struct, which is alloc defined here. And it's about what you would expect. We have some stuff around our branching, and then we come down, and then raylib starts logging stuff, which is cool, dynamically loaded. And let's close it so we can finish compiling. And then we can see here the back end of our compiler. I was just doing ABI stuff, so we can say, hey, the ABI mapping for this type is pass a struct by pointer with no copy, because it's more than this is more than 2 registers big. That's why that is. Struct by pointer, no copy. Yeah, it also might be because this is using my internal ABI and it doesn't need to do the system ABI. So you can see, you know, this is just like debug printing that we'll remove from the back end of the compiler. You can see we're generating a big old constant here. I have plans to make this smaller. This is our allocator stack. There it is again. Not sure why. Marshalling. Interesting. Oh, yeah, because we just log it. Okay, well, you know, I'll just keep scrolling down to get through the rest of our backend. And now we're running our color toggling program. It is actually supposed to be pink and purple because at runtime we are passing structs correctly. The structs, that color struct is the size of an int. It's 4 bytes, so it gets passed in a register. We can look at that. So this is going to be set color or something. We'll do declare. Right, draw text. So you may notice, whoops, that the type here, this is the struct color, which is 4 bytes, but it's typed here as an I64. That's just what Cling does. We know it's 32. We know it's 32 bits, but we declare it as an I64. You can see us here doing the ABI transformation where we're copying only 4 bytes into the register value that we ultimately pass to the function. So that is pretty neat. And to close it out, let's see what it returned. Term. So the runtime result was 1. So let's go, hey, the result was 10. So if you'll recall, when we run this function at compile time, it returned, it was returning 10, and then at runtime it was returning 1. And then that's what we saw. We saw 10 from the compile time execution at the end of linking, which is interesting. I would have expected that to print sooner since this took so long, but hey. Oh, it prints at runtime. So sorry. Yeah. At runtime, we're printing the result of the compile time execution. So by then it's actually a constant that's getting baked into the program. If we wanted to print the comp time result at comp time, we actually could do that. You know, we could just do it. You know, for now, the easy way would be just to make this a block of code. We could say let CT result, just like that, and then we're going to return CT result. And then we could say, hey, the comp time result printed at comp time, by the way, was CT result. Okay, so then we'll do both. And then saving opens a window. We get a random color every time because it's just the low bits of the pointer, which is kind of fun. And we got an info here because we're printing something at compile time. Hey, the comp time result printed at comp time, by the way, was 10. And if that's 11, then when we save and close our window, and go check our diagnostic, and we're going to see that it's 11. So having all sorts of fun, and then we'll run again, close our window twice, and then search for hey. We'll see we're getting 11 now. Yeah, hopefully enjoyed that demo of compile time execution. It is unlimited in its power, which should enable some really fun metaprogramming techniques. The intent is not just to run a game at compile time, but to generate all sorts of like really nice code at compile time and do some other things too. So